Hello, everyone, and welcome. I'm Matsaini bin Khaton, and this is our MEC111 explainer. Today, we're getting right to the heart of it all, the absolute foundation of engineering mechanics. We're talking about the three simple laws that literally dictate why a skyscraper stands tall or a bridge doesn't collapse. Yep, we're diving deep into Newton's laws of motion. So, if you remember from our last session, we talked about the principle of transmissibility. You know, the idea that whether you're pushing this car or pulling it, the effect on the car is the same, just as long as that force is along the same line. It's a really handy tool for simplifying our diagrams, but that kind of raises a bigger question, doesn't it? We know how to draw and move forces around, but what are the fundamental rules they all have to play by? What actually determines if that car is going to move, or, and this is way more important for us in statics, how does it stay perfectly still? Well, that's exactly what we're going to unpack today. So here's our game plan. First, we'll talk about why these laws are the bedrock of mechanics. Then, we'll break down each of the three laws: inertia, the one about equilibrium, and action-reaction. And for each one, we'll see how it ties directly into statics, before we wrap it all up with a summary at the end. Okay, let's jump in. Section 1, the foundation of engineering mechanics. You can really think of these three laws as the pillars that hold up everything else we're going to learn. And here they are, all in one place. You've got the first law, which is basically about an object's desire to, well, do nothing. The second law is about what it takes to change that. And the third law? That tells us that forces never act alone. They always come in pairs. These three together give us a complete framework for analyzing pretty much any force system. So let's tackle the first one. All right, Section 2, Newton's first law, also known as the law of inertia. Now, in general physics, this law covers any kind of constant motion. But for us, as statics engineers, it defines our number one goal: designing structures that stay perfectly absolutely still. So here's the formal definition. It says a particle will stay at rest or in its state of constant motion unless it's acted on by an unbalanced force. And I want you to really focus on that last part, unbalanced force, because that is the key to everything. To put it in really simple terms, it's something we all know intuitively. An object at rest, like this person relaxing in a chair, isn't going to just get up and move by itself. And something that's already moving will just keep on moving unless something else gets in its way. This resistance to a change in motion, that's what we call inertia. And this right here is where it becomes absolutely critical for statics. Look at this block. It isn't moving. Now why? It's not because there are no forces on it. Oh no, there are plenty. It isn't moving because all the forces are perfectly balanced. The downward pull from its own weight, which we've labeled W, plus any other force pushing down, P, all of that is being perfectly canceled out by the upward push from the ground, which we call the normal force, N. The net result? 0. So, here's a question for you. Think about a huge bridge with cars and trucks driving all over it. Why does it just stay put? Well, it's Newton's first law in action on a massive scale. That bridge is staying at rest because every single downward force, from the weight of the steel to the cars on top, is perfectly balanced by the upward forces coming from its support columns. This idea of balance leads us perfectly into Newton's second law. You see, while the first law tells us what we want, a state of rest, the second law actually gives us the math to make it happen. It explains what happens when forces are not balanced. This brings us to probably the most famous equation in all of physics. F equals ma. All it's saying is that if you have an unbalanced force, F, acting on an object with some mass, m, it's going to cause that object to accelerate, a. The more force you apply, the more acceleration you get. Simple as that. This governs everything from a ball flying through the air to planets orbiting the sun. But, and this is a huge but, here's the twist for statics. Our entire job as engineers in this field is to design systems that do not accelerate. Ever. We are obsessed with making sure that the acceleration is always 0. And this is the big aha moment. This is where dynamics becomes statics. Just think about it. If we take that universal law F equals ma, and we apply our special condition for statics, that acceleration a has to be 0, well, what happens to the equation? Anything times 0 is 0. So if a is 0, then the force, or rather the sum of all forces, which we write with the symbol sigma F, it has to be 0 too. And that, right there, is the single most important idea in this course, the condition of equilibrium. The sum of the forces equals 0. It's not just some arbitrary rule. It's a direct mathematical consequence of Newton's second law when we have no acceleration. And that's why we can break it down into components, right? The sum of all the forces in the x direction must be 0, and the sum of all the forces in the y direction must also be 0. These two little equations are the heart and soul of statics. So let me ask you this to let it sink in. What does it really mean for a building or a bridge when its acceleration is 0? It means it's in equilibrium. It means it's stable. It's not moving, it's not breaking, it's not collapsing. It's doing exactly what we designed it to do. Okay, so we've got the goal from the first law, stay at rest. And we've got the math from the second law, sum of forces equals 0. But how does a structure actually do that? How are all those forces actually balanced out? That's where Newton's third law comes into play. It's the mechanism behind equilibrium. Now, you've probably heard the simple version. For every action, there's an equal and opposite reaction. The more formal definition just adds a little detail. These forces between two interacting things are always equal in magnitude, opposite in direction, and they act along the same straight line. The classic example everyone uses is a rocket. It's a good one. The rocket engine pushes down with incredible force on the hot gas. That's the action. And in response, those gases push up on the rocket with an equally incredible force. That's the reaction. That's what lifts the whole thing off the ground. So how does this apply to something that's not moving? Let's look at this truss frame. Focus right here on joint B. The diagonal support, member BC, is pushing against that joint. We can call that the action. Well, at the exact same time, the joint is pushing back on member BC with an equal and opposite force. That's the reaction. And this little action-reaction dance is happening at every single connection, in every single member, and it's how the forces get distributed and balanced throughout the entire structure. So this leads to one last question for this part. Why is it that in all our diagrams and all our analyses, forces always seem to show up in pairs? You have a weight pushing down and a normal force pushing up. You have tension and a cable pulling on two different points. Why? It's because of Newton's third law. You literally cannot have a force by itself. Every single push or pull is an interaction between two objects. All right, time to put all the pieces together. Let's summarize what we've learned. So here is the entire story of statics in a nutshell. Law number 1, inertia, sets our engineering goal. We want things to stay put. Law number 2, F equals mal, gives us our magic wand, our core equation. When there's no acceleration, the sum of all forces must be 0. And law number 3, action-reaction, explains how it all works, how every push from a support and every pull from a cable creates an equal and opposite force to keep the whole system in perfect balance. It really is a complete, elegant system. So now we have the fundamental rules of the universe on our side. The next step is to get really good with the vector methods we need to apply these laws and start solving for unknown forces in real, complex structures. Thank you so much for joining me today. I will see you in the next one.